All about weather, specifically here storms and forecasting. We've talked a little bit about weather phenomenon already in Chapter 8, and now we're going to be looking at some specific things such as in the first section here, thunderstorms, lightning, and tornadoes. We will also be talking about hurricanes later on in this chapter, as well as some forecasting equipment. So the first phenomenon we're going to look at is thunderstorms, probably one of the most common ones around the world. Thunderstorms occur in all parts of the world. And thunderstorms are localized storms involving lightning, thunder, strong winds, heavy rain, and sometimes hail or tornadoes if the conditions are right. And like I said, these are common. Meteorologists calculate that about 2,000 thunderstorms occur around the world at any given moment. Each year, approximately 16 million thunderstorms occur on the Earth, and around 100,000 of those are here in the United States. Several conditions work together to produce thunderstorms, and it begins with a strong updraft. And we have to get that strong updraft, we have to look at air conditions here, and we have two terms here, stable air and unstable air. Stable air is under normal conditions. Currents of rising air are stopped by adiabatic cooling, and therefore do not rise to great altitudes. They go up quite a ways, but there is a definite point where they stop. That's stable air. However, in the right conditions, we can have unstable air. This is warm air near the ground, but very cold at higher altitudes. The rising air remains warmer than the surrounding air, and since it is warmer, it continues to rise to an even greater height than normal, allowing it to reach those greater heights. And this can lead to the development of thunderstorms. And we have really three stages of thunderstorm development. The first one is cumulus stage. This is where a steady supply of warm, humid air combines with those strong upward movements of the updraft, forms a billowing, rapidly growing cumulus cloud. Inside the upper levels of the cloud, ice crystals and supercooled water droplets begin to develop, creating the conditions necessary for an electrical storm, thunderstorm with lightning and so on. The mature stage is the arrival of precipitation at the Earth's surface, so when it starts raining, basically, unless it's hailing instead. But that precipitation, when it reaches the Earth's surface, that's the mature stage. This is the peak of the thunderstorm strength. There are heavy sheets of rain, accompanied by lightning flashes. Hail and tornadoes can develop in these kind of things. Now, this isn't a stage, but it is a feature, or it can be a feature of the mature stage, and that is a downburst. These are very strong localized downdrafts that create concentrated blasts of cool wind that can blow downward at 130 miles an hour or more. So this is actually a vertical column of air, basically, just blasting the ground. Downbursts have been known to level crops, damage buildings, topple trees, so these can cause quite a bit of damage depending on what's around it and how it blasts out there. Smaller but intense downbursts are called microbursts. And then we get to the third stage, which is the dissipating stage. The updraft disappears, the cloud begins to evaporate, it no longer has that moisture coming up into the cloud with that updraft gone. The precipitation tapers off. Again, there's no refilling of the moisture content. The downdrafts grow weaker, and eventually the whole cloud just disappears. Now, as these thunderstorms form, we can get there is the updraft system, and if it's just one updraft system, or an updraft system, is called a cell. Thunderstorms can have one cell or many cells. Most thunderstorms have several cells working inside them to supply with moisture, which is why a thunderstorm can last for hours in some instances. A squall line is a long line of advancing thunderstorms, usually moving ahead of a cold front. So this could create a wide area for thunderstorm activity. The supercell is a fierce single updraft giant. Supercells usually occur during the spring and early summer. Pictures of them are quite popular on social media now, and they are actually pretty cool looking. as far as picture goes. Supercells may tower to 65,000 feet, form microburst hail, continuous tornadoes. Supercells are usually from 5 to 10 miles in diameter, so as a storm goes, really not that big. Pronounced anvil or mushroom shape, we kind of talked about that shape, especially the anvil shape with the forming of cumulonimbus clouds in the last chapter. Now, a common feature in these thunderstorms is lightning. Our book's definition of lightning: an abrupt discharge of electricity through the air that produces a quick flash of bright light. We're going to look at lightning formation. I do have a picture of it. It's on the next, I think it's on the next slide, to show where some of these things will occur at. But for right now, the terms: we have a stepped leader. This is a barely visible stream of electrons that moves jerkily toward the ground in a series of steps. You see a photograph of a fairly intense lightning storm. It may capture stepped leaders. They're not even anywhere near as bright as a real lightning bolt because we just don't have the energy moving through them yet. The positive streamer, so the stepped leader comes from the clouds. The positive streamer comes from the ground. Positive charge on the ground that rises, attracted by the approaching stepped leader. Opposite charges attract to each other. So we have the negative charge in the cloud. It starts attracting the positive charge in the ground, and they start moving through the air to meet each other. When they meet, that's when we get a return stroke. When a stepped leader meets the positive streamer, a huge current of positive charge surges upward from the ground to the cloud and forms a brilliant flash of light. And when we say huge current, we mean an absolutely phenomenally large amount of current. Let's see. It only lasts a few millionths of a second, but the power flowing through it typically reaches 2 trillion watts, or 2 billion kilowatts. The tremendous rush of charged particles heats the air in the return stroke. We'll talk about that effect a little bit later on. But yeah, so I mean, a phenomenal amount of electricity. But people survive it. People who have been struck by lightning, they're messed up. They got burned. Depending on the path the lightning went through their body, can determine how much nervous damage they might have. But people do survive it. So let's see, the dart leader. This is a phenomenon where it travels down the channel of the first strike, initiating a second return stroke. So it's pretty much in the same spot. As many as 20 dart leaders return stroke combinations may occur in less than a second, giving the appearance of a single flickering bolt. So when you look at the lightning bolt and it looks like it's a strobe lightning bolt, basically, it's most likely several of these dart leaders following after that first return stroke, initiating several more strokes. Now, let's see, I believe on the next, yep, we do. Okay, here we have a diagram of what's going on there. Ice and water particles separate in the cloud because of the wind and everything. Charged particles are getting separated. You see the positive at the top, negative near the bottom. Negative charges are attracted to the earth. Positive charges in the form of this darker orange going up from the ground, meeting that stepped leader. Once they meet, bing, a massive amount of electricity moves from the cloud to the ground, and the two joint hitting the ground there. So just a little bit of a diagram showing how that kind of works out. Thunder, remember I said that we talked about that heat formed by the electricity moving through the lightning bolt? Well, here's where we're talking about it. It superheats that air around the bolt to something like 54,000 degrees. Yeah, 54,000 degrees Fahrenheit or around there. And all of that heat suddenly shoots upward, creating a vacuum. And then as that air fills in that vacuum there, it creates that booming sound of thunder, which is just a shock wave of sound. And we just talked about that. Causes their heat from the return stroke, causes the air near the lightning bolt to expand explosively. Because light travels faster than sound, a lightning flash is seen before the thunderbolt is heard. And you can kind of tell, well, actually you can tell if a thunderstorm is moving towards you or away from you by counting the seconds. You see the lightning bolt, 1, 1,000, 2, 1,000, 3, 1,000. There's the thunder. Another lightning bolt happens, 1, 1,000, 2, 1,000. You hear the thunder. You know it's getting closer to you. I enjoy sitting outside under a porch during thunderstorms, and when that lightning and thunder are almost right on top of each other, that's when the thunder is, or that's when it's happening right above you or right over you. And then you can find as it's moving away, when the duration gets longer. If you're really savvy and you're keen to do it, you can actually figure out how far away the lightning strikes by utilizing the speed of light versus the speed of sound. You can actually figure out if it's, I think it's something like 2.5 seconds is 1 mile, give or take. No, it takes 10 seconds for you to hear the thunder from a lightning bolt, and the lightning occurred 2 miles away. So about 5 seconds per mile there. So, yeah. Types of lightning. Now, the kind of lightning we've been talking about is that negative cloud-to-ground lightning. There can be positive cloud-to-ground lightning. Usually, remember that positive charge at the upper part of the cloud. Sometimes that will be attracted to negative charges in the ground. We get that positive cloud-to-ground. There's also ground-to-cloud lightning. The electricity is actually going up into the cloud there. And we can have cloud-to-cloud lightning. That's actually fairly common. Sometimes you might see that if you're flying in an airplane descending through a storm, you might see some of that cloud-to-cloud lightning. And then even rarer here, one of the rarest, is called ball lightning. Rare phenomenon that consists of a small sphere of electricity that seems to float in the air for several seconds. Although this type of lightning has been seen by a variety of people, scientists do not understand what causes it to form. Basically, we have stories about ball lightning, but it hasn't really been studied yet. So we really don't know the circumstances that cause it to form into a ball instead of moving from point A to point B like all the other ones. So, yeah. And here's a diagram of several of those different types. We have cloud to ground here, both negative cloud to ground. Nope, we don't have any positive. I thought we did. But we have cloud to ground within one cloud, cloud to cloud. We have cloud to air. Usually it doesn't go just to the air. I mean, it does, but that's not as common as, say, cloud to cloud or even within the same cloud. Because you have these positive and negative charges that are a lot closer together, and air is a horrible conductor of electricity. Just by the nature of lightning moving through air, you know it has to be tremendous volumes of electricity because air is a horrible conductor for electricity. So just the fact that it moves means that there's a huge amount. And usually lightning is going from point A to point B. Like I said, the phenomenon where it doesn't go from one to another is not as common. They're pretty rare. So go ahead and answer the science video question 9.1a. And that way I know that you have watched this video and you can get the points that are appropriate for watching this video.